Hey everyone, I'm absolutely thrilled you're joining me for today's explainer. If you've ever, just glanced at a physics textbook and felt that immediate wave of dread, yeah, you are definitely in the right place. Today, we're going to take what looks like a deeply intimidating complex physics concept and turn it into something fun and easy to digest. We're breaking down Bernoulli's equation, so let's jump right in.
Think about this for a second. How does a heavy airplane actually fly? I mean, it's a literal massive metal machine, right? Weighing hundreds of thousands of pounds, packed with people and luggage, and yet it just gracefully lifts off the runway and glides through the air. It kind of feels like magic. But, well, the secret isn't magic at all. It's actually down to a remarkably simple rule of fluids. And the best part? To understand it, we don't even need to step foot in a lab or a wind tunnel.
Section 1. The water slide effect. Instead of a lab, I want you to imagine we're heading to a water park. Picture yourself at the very top of a massive water slide. Now, pay attention to the physical sensations of that ride, because they perfectly map to the three types of energy we're tackling today. So first, you start way up high, right? Just by standing up there at the top of the stairs, you have high potential energy. Then you push off. As you speed up, rushing down that slide, your kinetic energy, that's your energy of motion, goes up, and all the while, you can physically feel the water pushing around you, right against your body. That push, that's pressure energy. So we've got potential, kinetic, and pressure. Just hold on to those three ideas for me.
And that brings us straight to Bernoulli's equation. In plain English, it just says that the total energy stays exactly the same, as long as no energy is lost. It's kind of like a perfectly balanced budget. On that water slide, your potential energy, your kinetic energy, and your pressure energy, they're constantly shifting and trading places with each other as you twist and drop. But if we pause time and add them all up at any given moment on that slide, the total sum of those energies remains perfectly constant. The whole shebang stays balanced.
Which brings us to Section 2, the PVH memory trick. Now, if you crack open a textbook, you're going to see this terrifying formula. P plus 1/2 rho v squared plus rho gh equals a constant. Whew, I know, just looking at a bunch of Greek letters and squared variables is enough to make anyone's brain want to shut off. But remember, this massive formula literally just represents the pressure energy, kinetic energy, and potential energy we just felt on the water slide. And like I promised, we are going to simplify this right now. We are going to ditch the scary algebra and break this down using a super simple memory trick. PVH. P stands for pressure, V stands for velocity, which is really just a fancy word for speed, and H stands for height. PVH. By just focusing on these three straightforward things, pressure, velocity, and height, we can totally understand the physics here without needing an advanced degree. So what's really fascinating here is how these three things interact. Remember that balanced budget we talked about? Because the total energy has to stay perfectly constant, these variables act exactly like a seesaw. If one side goes up, another side absolutely must go down to keep the whole thing balanced. So, for example, if your velocity goes up, your pressure goes down. They trade off. It is a constant balancing act. Section 3. Real-world Bernoulli. Okay, let's step out of the theory for a second and look at a super practical application. I'm willing to bet almost all of you have actually done this. Step 1, you've got a normal, steady flow of water coming out of a garden hose. Step 2, you decide you want to spray your unsuspecting sibling all the way across the yard. So what do you naturally do? You jam your thumb right over the opening. Let's think about what physically happens when you do that. This little backyard prank brilliantly illustrates our PVH rule in action. When you put your thumb over the hose, you're making the opening smaller, right? Now, for all that water to still squeeze through, it has to rush out much, much faster. So boom, our velocity just went way up. But what does our seesaw rule tell us? Here is the absolute crucial point. If the velocity goes up, the pressure has to go down. The water is shooting out way faster, which means the actual pressure right there at the opening drops. Faster velocity means lower pressure, always. So let's bring it all full circle back to our opening mystery. What about that airplane wing? How on earth does this PVH seesaw, the exact same one governing our garden hose, keep a massive metal jet up in the sky? Well, it all boils down to the clever shape of the wing and how it forces the fluid, which in this case is the air, to move. The way an airplane wing is curved actually forces the air moving over the top to travel faster than the air moving underneath it. So the velocity of the air on top goes up. And thanks to Bernoulli's equation, we know that when velocity goes up, pressure has to go down. This creates a literal zone of lower pressure sitting right above the wing. Because the pressure under the wing is now relatively higher, it physically pushes the airplane upward into that lower pressure zone. And guys, that is lift. It's literally just trading velocity for pressure. How cool is that? Section 4. Test your fluid knowledge. All right, you've mastered the water slide, the PVH trick, the garden hose, and even airplane wings. So let's make this a little interactive. Quick quiz number 1. Based on everything we just covered, why does an airplane wing generate lift? Think back to that balancing act. I'll give you a second. Did you get it? It's because the faster air above the wing lowers the pressure. You get that super high velocity over the top, which perfectly trades off for lower pressure. And that allows the higher pressure underneath to just lift the whole plane right up into the sky. Absolutely brilliant. Okay, let's really cement this in with quick quiz number 2. What happens to pressure if a fluid's speed or its velocity increases? Think about your thumb over that garden hose. When that water suddenly speeds up to blast your sibling, what happens to the pressure at the opening? Take a guess? Nailed it. It decreases. It is the ultimate seesaw effect in action. The total energy has to stay constant, so if speed goes way up, pressure absolutely has to go down to maintain the balance. Honestly, you've officially mastered the core of Bernoulli's equation. Now, I want to leave you with a thought to chew on. Where else is this PVH balance happening in the world around you right this very second? Because once you grasp the velocity and pressure are constantly doing this intricate little dance to keep energy balanced, I promise you, you're going to start seeing it everywhere. From the way the wind howls as it squeezes through a narrow alleyway, to how your shower curtain mysteriously gets sucked inward when you turn on the hot water. It is all the exact same beautiful physics. So keep your eyes open for it out there.